Hi students, this is a run through of the TR55 homework assignment. I'm going to go through the homework. I'm going to use a different watershed than the one that's indicated in the homework assignment so that I get different answers, but all the steps will be the same. So if you follow along and do the steps that I do in the video, it should give you a good leg up on completing the homework assignment. So the first step that you're going to do in your homework is you have to delineate a watershed. And we're going to use stream stats to do that. You're going to use this pair of coordinates as the outlet for the watershed that you're going to delineate. Like I said a moment ago, I'm going to use a different watershed. So I'm going to go to stream stats. And I'm going to zoom in. I'm going to pick a watershed that's on the New Jersey side. Your watershed will be on the Pennsylvania side. But I'm going to focus in on the area around Phillipsburg, New Jersey, which is just across the river from pretty close to the site that will be part of your homework. And remember, when we zoom in to stream stats, we've got to select the data that is behind the map. So I'm going to pick the Delaware River Basin data set. So I am going to use Lopatcong Creek as the watershed that I'm going to delineate. So as a reminder, you're going to zoom in until the stream gets this blue pixelated look. That lets me know that I'm zoomed in enough that I can delineate the watershed. Once I'm zoomed in that amount, I click on delete, and then I will put my cursor over the stream whose watershed I want to delineate, and click. When the watershed is done delineating, it will draw the shape of the watershed on the map. Remember that this doesn't always necessarily work the first time, so if it fails to delineate the watershed on your first attempt, try it a few more times. Once you've delineated the watershed, you're going to come over here to the Continue button and click on that. And you're going to select basin characteristics. So the two basin characteristics that you need for your homework are drainage area, so you're going to pick that one, and the percentage of developed land, essentially. And that one is LC06dev, and you're going to select that one as well. And once you've done that, you'll scroll down to the bottom and click on Continue. Once you've done that, you can click on Open Report, and it will give you this report that's generated. And in that report will be the drainage area and the LC06dev. Now, I tried this earlier today, and I noticed that I had to do all these operations a couple of times to get them to work in stream stats. So again, if things don't work out at first, that's okay. Just keep at it, and you will eventually get it to work. So we're going to copy this information to our spreadsheet. So we need the drainage area, 16.3 square miles, and the LC06dev, which is 9.35%. So I have a spreadsheet open, and so I am going to put that information in. And that LC06dev was 9.35%. I'm going to make this spreadsheet bigger so that it's easier to see. And I'll put the units in here as well. So since I have this LC06dev is the developed land, and I can also compute the undeveloped land as a percentage. And that is just going to be equal to 100% minus that percentage of developed land. And so we've got 9.35% developed land and 90.65% undeveloped land. Now, I'm also going to translate all of these areas into units of acres. We're going to use acres later. We actually don't need them for this part, but we will need them later on. So I'm just going to look up the units conversion for that. So I want to know acres per square mile. And that's 640 acres per square mile. So equals that value times 640. So 10,432 acres. I also want the acres of my developed and undeveloped land. So I can take those percentages and I can multiply them by that total area to get the developed and undeveloped land. So I'm going to say developed acres and undeveloped acres. And my developed acres will be equal to this percentage divided by 100, so it's an actual percent, times that area. And my undeveloped acres is going to be equal to that percentage. Oops. Divided by 100 times this area as well. So I've got 975 developed acres and 9,000 something undeveloped acres. I'm going to insert some blank lines below this because we're going to need a lot more space in the second part of the assignment. So, and again, we'll come back to that in a little bit. So once I have my areas in my spreadsheet, one of the first things that I want to do is I want to compute a composite curve number for my watershed. And I'm going to use these area ratios to do that computation. So if I go back to our assignment, I'm going to use this document here, TR55. And once I've loaded that, I'm going to scroll to the beginning of Chapter 2. So Chapter 2 is where all of my equations are that I'm going to use in a little bit, and then also the curve number tables. So the curve number tables take up a couple of pages. It starts with table 2-2A and 2-2B and 2-2C and D. So if I look at my homework description, I see that it says here that I should assume that the portion of the watershed classified as LC06 Dev is best described as urban district, commercial, and business. So that's the value that I'm going to use. So I go to TR55 to those tables, and I'm looking for that urban district, commercial, and business. I see that here. Here's urban district, commercial, and business. In the homework assignment, it says that I'm to assume that I have soil type C for the entire watershed. So if I look in TR55, here's soil type C up here, so it's that column. Here's the urban district, commercial, and business. So my curve number for that subportion would be 94. So I'm going to put that in the spreadsheet. I'm going to add a curve number column here. And so for my developed acres, that has a curve number of 94. Going back to the homework assignment, it says that the portion of the watershed not classified as developed is best described as woods, grass combination in fair condition. So again, if I go back to TR55, I don't see that description on this table, so I'm going to look at the other tables. And here we see woods, grass combination, fair condition. Again, it will still have a soil group of C, and so my value for that would be 76 for that subportion. So if I go back to my spreadsheet, my curve number there is 76. Now I'm going to compute a composite curve number. I'm going to actually put that all the way down here because in the second part of the assignment, I'm going to use this extra space to put in some additional curve numbers. But here I'm just taking the proportion of the area that each curve number applies to and use that as a weighting to come up with a composite curve number. So that will look something like this. It will be equal to, and I'm going to use lots of parentheses to make sure I get the order of operations correct. But it's going to be equal to this developed area times my developed area curve number plus this developed area, or pardon me, undeveloped area times my undeveloped area curve number, all of that divided by the total of my two areas. So that area plus that area. And that will give me a curve weighted, area weighted curve number. Now, if I did this correctly, what I should get from this equation is a curve number value that is somewhere in between 76 and 94. It should be in between those two. Because I have a lot more area that is undeveloped, my result should be closer to 76. So what I'm expecting to see is a curve number that is a little bit higher than 76. And that's what I got. I got a composite curve number of 77.83. Once I have my composite curve number, the next thing I'm going to do is to download the precipitation data. So again, if I go back to this page in Drexel Learn, and this link right here, the PA State Climatologist link, I'm going to click on that. That'll open up this page. From here, I click on Data, and then View Download, and this will give me a selector page. I have to choose the data format of my data, and I happen to know that I'll be looking for FAA daily data. That's data that is collected at airports and summarized for each day. So I click on that. If I go back to the homework assignment, it says here that I should be using 1 year of recent rainfall daily totals from Mount Pocono Airport. Mount Pocono Airport is in the vicinity of our watersheds, both the watershed that I'm doing here and the one that you're going to do for the homework assignment. So if I go back to the PA State Climatologist website, to that page, I'm looking for Mount Pocono. Here's Mount Pocono right here on this row. So I'm going to click on that link. And here I get to specify the beginning and ending date of my data. I'm going to use a recent year. I'll pick 2023. You can use a different date or a different year, but 2023 should be fully complete and is relatively recent. So I'm going to pull a full year's worth of data. So it's going to start January 1st of 2023, 2023-0101, and end 2023 December 31st. And I only need the 24-hour precip data, so I'm going to check that checkbox. I'll download the data as a CSV file, and I'm not going to include the metadata. You can if you want, but I'm going to skip that. Once I click the Submit button, I can see that it has loaded that data set into my Downloads folder. I'm going to open that up. Give it a second to open. And so here is our precip data. So I'm going to copy and paste this data onto that other spreadsheet. And I'm going to paste it kind of below this other material at the top. So I'll paste it right there. All right, I've got my precip data. And now I can start to actually incorporate some of the equations from TR55. So again, if I go back to the homework assignment and I go back to my TR55 document, I think I've got that open elsewhere, and I'm going to go back to the beginning of chapter 2. So all of my equations here are on this first page of chapter 2, and this is page 2-1. And my main runoff equation is here, but I'm not ready to put that equation in yet. I'm actually going to compute two intermediate values, and the two intermediate values that I'm going to compute are my S value, and S is the potential maximum retention after runoff begins. And I'm also going to compute my initial abstraction. So my S value is equal to 1,000 divided by the curve number minus 10. So I'm going to put that in my spreadsheet. And I'll put that over here. So again, that is equal to 1,000. And I'm going to put that first part in parentheses to make sure that I get order of operations correct, divided by my composite curve number. So very important to use the composite curve number. That minus 10. And I get a value of 2.87 and change. And then my initial abstraction, I sub A. And again, from TR55, initial abstraction is equal to 0.2 times S. And S was the value above it. So my initial abstraction is 0.57 and some change. All right, so now that I'm gonna put S and IA up here because I only actually need to calculate those once. Those are not going to change day by day. But my runoff and my precipitation will change day by day. So now I'm ready to go ahead and put in my first Q equation, my equation for runoff. And so I'm going to call that Q raw, because as we'll see in a moment, I'm going to get values here that don't make sense. And I'm actually going to have to do some adjustment to make those values make sense. So I'm going to make this a little bit smaller so that I can see my S and IA values up here. And so going back to TR55, that equation is equal to P minus initial abstraction squared, and that's the numerator. So I'll put that part in first. So P, precipitation, is the 24-hour rainfall total. We're going to do that day by day. So that information is the next column to the left. So that would be right there. That minus the initial abstraction, which is this value here. Now, for the initial abstraction, I'm always going to want to refer back to this cell, right? I'm going to drag that equation down to the bottom of the spreadsheet, but I don't want this cell to move downward. I always want it to the equation to return back and use just the value in this cell. So to ensure that I do that, I'm going to use the F4 function. On my computer, it's actually function F4. And I press that, and what it does is it puts these little dollar signs into that cell reference. And those dollar signs let Excel know that to always look back to this exact cell. It's not a relative cell, it's exact. So I have that. Close parentheses. I'm actually going to put another parentheses, open parentheses at the beginning of this, and I'm going to raise that whole value to the power of 2, and then close parentheses. So that's the numerator part of the equation. If I look back at TR55, the denominator is precip total minus initial abstraction plus the value of S. So again, coming back to my spreadsheet, so all of that divided by, and again, 2 parentheses, P, so that value again, minus initial abstraction, or this value up here. And again, it's the function F4 version, so it puts the little dollar signs in. And then, let me double check the equation, plus the value of S. So all of that plus this value of S. Again, I don't want a relative reference. I always want it to point back to this cell. So function F4, to put the dollar signs in and close parentheses. So once I have that typed in, I can double click the little box that is in the bottom right-hand corner, and it will copy that equation to all the lines in the data set going down to the bottom. And it's going to change the relative reference for that precipitation value. So for precipitation on this row, it's going to look in this box, and this row, it's going to look in this box, and so on. Now, one of the things that you'll notice right off the bat is we have a weird result here. So on days with no rainfall, when we have 0 precipitation, that equation is still giving us a discharge value. So the reason for that is this equation is actually only valid when my precipitation total for that day is more than my initial abstraction. You can think of initial abstraction as like a cup on the landscape, and the rainfall has to fill up the cup before it can start to discharge. So we've got to have, this only works for precip that is greater than that initial abstraction value. So I'm going to add a new column here, and I'm going to call it Q actual. And I am going to use an if equation to indicate whether or not we have a value for discharge. So that equation will look like this, equals if open parentheses, the precip value, so I'm going to toggle over 2 columns, if that is greater than my initial abstraction value, and again, function F4, so that I put the dollar signs in there. If precip is greater than initial abstraction, use the Q raw value next door. Otherwise, use 0. So what this equation is saying in English, if precip is greater than initial abstraction, use that value. Otherwise, my runoff value is 0. If I have 0 rainfall, I have to have 0 runoff. And if I typed that correctly, since I had no precipitation on January 1st, 2023, it better give me a 0. It did. In the next row, that value is also less than the initial abstraction, so it better be another 0. It is. But on January 3rd, I have a precip total that's greater than the initial abstraction. So when I pull this down, I better get a non-zero value. And it worked. So I got a non-zero value there. So that gives me some indication that I put the equations in correctly. So now I can just double click on that little box in the corner, and it will copy that equation all the way down to the bottom of the data. And I'm going to scroll down and look for other instances where I've got precip greater than my initial abstraction and make sure that I'm getting a non-zero value for runoff. And I am. I see a couple of instances where I have values greater than my initial abstraction, and I'm getting non-zero values. Now, the discharge value from that equation is runoff in inches. It's a depth of runoff. That is not how we normally think about runoff. We normally think about runoff as a flow rate, something like cubic feet per second. So I'm going to do some units conversions to get a runoff value in cubic feet per second. So to do that, I'm going to modify my spreadsheet a little bit. I'm going to change this from developed acres to developed area and undeveloped acres to undeveloped area. And I'll put my acres units over here. And I'm actually going to want to compute those areas as square feet as well. So I'm going to put a new column here. Let's see, I'll put it all the way over here. So I'll put just so I don't kind of get things all jumbled up over here. So first I'm going to look up to see how many square feet per square mile. So I can and my answer to that is about 2.78 times 10 to the 7th square feet per square mile. So I'm just going to copy that, bring it over to my spreadsheet, and I'm actually going to insert a row here and move this up here. All right, so my area in square feet is going to be equal to that 16.3 square miles times the conversion factor that I thought I copied. Let's try that again. All right, and so I have many, many square feet in that 16.3 square miles. I'm actually going to use the percentages here to estimate the square feet of developed and undeveloped land. So do I need to do that? No, I don't need to do that. I actually just need this number of square feet. All right, so my Q, I'm going to add a new column that is Q actual cubic feet per second, right? So I'm going to do the units conversion there. So remember that I've got a depth in inches and I've got an area in square feet. So I want to convert that depth in inches to a depth in feet. So this equation is going to look like this. Equals, open parentheses, that value, which is depth in inches, divided by 12, which will make it a depth in feet. And I'm going to multiply that by my drainage area, my total drainage area, and that'll be this value up here. And again, I'm going to do the function F4 so that I'm always pointing back to that value. And that will give me my cubic feet of runoff. But then I have to divide by the number of seconds in a day. So I'm going to, in my equation, I'm going to actually rearrange things a little bit and type times 1 divided by, and I looked up earlier, there are 86,400 seconds per day. So I've got feet times square feet divided by seconds per day. So that will give me cubic feet per second. Now in that first row, my Q actual is 0. So my Q actual in cubic feet per second also better be 0. And it is. And as I start to drag this down, On this non-zero discharge row, I get a value that's non-zero. So again, that seems correct in both instances. So I'm going to double click to drag that down to the bottom. I'm going to do another units conversion. In a moment, the water quality data that we're going to look at is going to be in milligrams per liter. So I would actually like Q actual in liters per second. So I want to do that conversion as well. And to facilitate that, I'm going to look up how many liters per cubic foot. And there are 28.3 and change liters per cubic foot. So I'm going to just copy that. And again, for the units conversion here, I can just say that my liters per second is equal to cubic feet per second times that conversion. By the way, in engineering, units conversions are the biggest opportunity to get things wrong. So you'll definitely want to be very meticulous about your units conversions and double check them. So I'm going to, again, double click that to carry that down to the bottom. And so now I have daily discharge rates in terms of liters per second. So the next thing I'm going to do is I'm going to go back to the homework assignment, and I'm going to open up this other document, this Pennsylvania BMP Manual, Chapter 8. And when that opens up, I'm going to scroll down until I get to the event mean concentration table. I happen to know what that looks like. All right, that's it right there. It's on page 9 of 46, and it's table 8.3. So I'm going to zero in or focus in on this, make this a little bit bigger. And so what this table provides is it provides total phosphorus event mean concentration. And remember, we said in class that an event mean concentration is an estimate of the concentration of a pollutant over the entire storm event. So over the first flush, which we assume is going to have more of the pollutant, over the tail end of the storm, which is going to have less of the pollutant. But again, it's a way of saying what is the overall average concentration for that pollutant over the storm. And it provides that information by different land use categories. So I'm going to find the land use categories that do a pretty good job of matching up to my developed and undeveloped land. For my undeveloped land, I'm going to assume that that is comparable to forest. That might not be exactly right, but it's a pretty good surrogate for that. And for my developed land, I'm going to assume that that is comparable to a medium traffic street. Again, that might not be exactly right, but it's pretty good. So I'm going to come back to my spreadsheet, and I'm going to add a TP and a TN value in here. So TP standing for total phosphorus. And actually, the nitrogen in the table was nitrate plus nitrate. It's not exactly total nitrogen or TN, but the majority of the nitrogen in total N would be nitrate plus nitrate. So I'm going to, as shorthand, I'm going to say that's pretty equivalent to that. And I'm also, actually, I'm going to move these up here because, again, I've got to use my developed and undeveloped land to specify those. So I'm going to move them over one more. All right, so in my my developed land, let's go back to, so in my developed land, my TP was 0.33 and my TN was 0.58. So there's developed land, 0.33, 0.58. And my undeveloped land, we said we're going to use forest. So that's going to be 0.15 and 0.17. And if you look at the values, you'll notice that we're getting more nutrient pollution from our developed land and less nutrient pollution from our undeveloped land. That makes sense. That's what we expect, but just pointing that out. All right, so now we also need to compute. I'm going to do some color coding so that I can easily match things up across the page. So now I've got to compute a composite value for my TN and TP. And again, I'm going to use areas to weight those values to come up with my composite TP and my composite TN. And so again, that's going to look like this. Equals the area for my developed area times my TP for my developed area plus my area for my undeveloped area times my TP for my undeveloped area. All of that divided by the sum of these areas together, or that plus that. And again, if I look at the sizes of the areas and the TP values, I better get a composite TP that is somewhere in between 0.15 and 0.33. And because I have so much more undeveloped area, that value better be closer to 0.15. So I should get a result that's just a little bit higher than 0.15. And I did, 0.166 and change. I'm going to do now the same thing for TN. And again, I get a value that's a little bit higher than 0.17, and that makes sense. That's what I'm expecting. So the units for these event mean concentrations are milligrams per liter, and I've got liters per second for discharge. So I can do a TP load, and that will be in milligrams per no, that'll be milligrams per second, and that's going to be equal to this discharge value times my TP value here. And again, we've got no discharge on that first day, so we get no TP load. And okay, I did something wrong. Oh, I know what I did wrong. So here I've got so I'm going to erase all that. All right, let's try that again. So it's going to be equal to that discharge times this concentration, but the thing that I forgot to do was do the function F4 that's always going to point back to that cell. So now when I double click it down, I do get a TP value that is for the days that I have discharge. I'll do the same thing for TN. Milligrams per second. And again, that's going to be equal to that Q actual in liters per second times my TN event mean concentration composite value function F4 so that it always points back to that cell. Now, when we think about pollutant loadings, we don't ever think in units of milligrams per second, but we might think in units of milligrams per day. So I'm going to do some unit conversion to get those loads in milligrams per day. So, and I'll do that as TP milligrams per day. And that's just going to be equal to this value times, times 86,400. We said there were 86,400 seconds in a day. And Tn, milligrams per day. And again, that'll be equal to that times 86,400. Now, you could convert milligrams to grams and get grams per day if you wanted to. You don't have to do that. I'm going to go ahead and do it just because, again, that would be a more standard units for pollutant load. So TP grams per day and Tn grams per day. And that will just be equal to these values. So this one for TP, there's 1,000 milligrams per gram. So it's going to be that value divided by 1,000. And again, right where we have discharge, so we're getting 187 grams per day during that event. And for this, it'll be equal to that divided by 1,000. Same idea. And then we could add together all of the loading over that 1 year. So we'll come all the way down to the bottom, and I'll say something like total load grams per year. And it's just going to be the sum of everything in that column above. And I can use the little sum symbol up here to compute that. I'm going to put in, I'll format these cells to use a comma separator and no decimal places. So I've got a little over 1 million grams of phosphorus and about 1,335,000 roughly grams of nitrogen. So all of this is my pre-development condition. So I'm going to label this sheet as pre-development. And now I want to do all the computation for post-development. But what I'm going to do is I'm going to use all of this. So I'm going to copy this whole thing. If I come all the way up to the top here and I click on that, I select everything, and I'm going to copy and put it over here and paste. And I'm going to call this tab post-development. So the good news is I don't need to redo everything that I did. I'm going to take full advantage of everything that I've already done. But what I do need to do is I need to add in the other facilities that are going to be part of my development, and I need to recompute my composite curve number, and I need to recompute my Tn and Tp event mean my composite event mean concentrations. So if I go back to the homework assignment, I can see that in this watershed, I am going to build a golf course that's 100 acres, a parking lot and driveway that's 4 acres, and a clubhouse, restaurant, and pro shop that are 0.8 acres. And all of this is going to be built in the undeveloped portion of the watershed. So I have to subtract these areas from the area of the undeveloped, right? So I'm going to add that into my post-development tab spreadsheet. So I've got my golf course. I've got my driveway, parking lot and driveway. And I've got my buildings. I'll just use the shorter term there. So my golf course was 100 acres. My parking lot and driveway is 4 acres. And my buildings are 0.8 acres. And I'm actually going to remove this, the undeveloped acreage, and I'm going to actually recompute that. So the undeveloped acreage is going to be equal, because remember, I'm subtracting out the golf course, the parking lot, and the building, because those are no longer going to be undeveloped. They're going to be a parking lot, a driveway, and a building. So my undeveloped acreage is going to be equal to what it was in the pre-development scenario, so equal to that value minus, minus this minus that minus that. And I hit enter, and so it's 9,351. I'm just going to compare that to what's on the other page. It should be less. Yeah, so previously my undeveloped area was 9,456. Now my remaining not undeveloped area is 9,351. It's a little smaller. That makes sense. That's what I would expect. And now I'm going to put in the curve numbers for those new land uses. So if I go back to TR55 and I look at the curve number tables, so all right, my very first one up here, open space includes golf courses, so that's good. I'm going to assume that my golf course is in fair condition. I don't have a strong reason for saying fair condition other than it's in the middle between poor and good condition. So, and again, it's soil type C. So for my golf course, I'll have a curve number of 79. My parking lot and driveway, if I go back to TR55, I've got impervious areas here, and it's got paved parking lots, roofs, and driveways, etc. That's what I want. So soil type C, that'll be a curve number of 98. And my buildings and roofs is also going to be a curve number of 98. It's all part of that same category, right? So remember, that's the higher the curve number, the more direct runoff we're getting from that land use. So that'll also be 98. All right, now I've got to recompute my composite curve number. So I'm going to recompute it right in this same cell right here. So all the places that I referred back to that cell, it's going to update the spreadsheet, and I can just use that information. So my new composite curve number, it's the same procedure. So it's going to be, and these are all acres, by the way, so I'll put acres in here. So here I'm just going to redo that whole equation. So that's going to be equal to, and it'll be that times that plus that times that plus that times that plus that times that plus that times that. All of that divided by the total area. And for the total area, I'm just going to use the sum. So all of that divided by sum open parentheses, and I can just highlight these areas. Now, remember, it's the total area, so I don't want to use these values up here. I just want to use the sum of the developed area, the undeveloped area, the golf course, the parking lot, and the building. So, and close parentheses again. Now, my previous curve number, I think, was like 77. It should be a little bit higher than that, probably not a whole lot higher, but something a little bit higher than 77. So yeah, a little bit higher, 77.72. In pre-development was 77.68. So a very small change in curve number, really. But again, enough to change some of the values in here. The other thing that I need to now compute is I need my TN and TP numbers for my event mean concentration. So again, if I go back to my event mean concentration table, here I've got a line item for golf course, so that's good. So my TP value will be 1.07, my TN will be 1.84. So 1.07, 1.84. So, and these values are quite a bit higher. So a lot more pollutant loading coming from my golf course. Now I'll look for, make this a little wider, look for my parking lots and driveways. So I'm going to assume that my parking lot, let's say, here's a parking lot layer here. Let's say, we're hoping that our golf course is going to be very successful, so we'll say it's a high traffic parking lot. So my TP will be 0.39, my TN will be 0.6. And let's look at our building roofs. Here we've got a rooftop category, that's convenient. And my TP and TN values will be 0.13 and 0.32. And now, again, I'm going to recompute my composite TN and TP values, very similar to what I did with the composite curve number. So I'm just going to delete that whole equation, and I'm going to redo that. So that will be equal to this area times that value plus 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 this area times that value, close parentheses, and then all of that divided by the total area. So divided by, again, sum close parentheses. And now I've got a TP value of 0.17. I'm going to do the same thing for TN, and then I'll check these values against the pre-development and make sure that the numbers that I'm getting here make sense. All right, so my new composite TN and TP numbers are 0.17 and 0.22. Under pre-development, it was 0.16 and 0.20. So I'm getting higher TN and TP event mean concentrations. Again, that makes sense. That's what I would expect to see. And if I come all the way down to the bottom, now my total load is 1,129 and change grams of phosphorus and 1,443 and change grams of nitrogen. And that is higher than what I had before. So again, that makes sense. And that's essentially it. So I hope you found this useful, and good luck on your homework, and see you in class.